Here we are given a 4 by 6 matrix, and we need to find a basis for the column space of this matrix A. We call that thus spanned by all column vectors of A. So the column vector, we have how many? 6 column vector, right? And each vector is a column vectors with 4 entries, right? So they are only R4 1, right? We can write R4 or 4 rows 1 column. Of R4 that is spanned by all columns vectors of A. Okay, so now how to do that? We will just transform this matrix to row echelon form or reduce row echelon form. Matrix to use elementary rows operation. Use elementary rows operation. We bring this matrix to either row echelon form or reduce row echelon form. Okay, and in this case, we get, here's a result. We get this matrix 1 0 0 0 0 1 0 0 3 minus 1 0 0 0 0 1 0 2 minus 1 0 1 0 3 minus 1 1 0. Okay, so this is a reduced row echelon form of A, but we can just keep it as reduced echelon form. We don't need to reduce it, so just row echelon form. We don't need the reduced version. Anyway, this is the row echelon form or reduced row echelon form we get. So let's comment on the two matrix. The column space of the two matrices are different. However, the dimension of column space of the two matrices are the same. They have the same dimension, but they don't have the same column space. So look at this matrix first. Let me call this a matrix A B. Okay, and we can easily find a basis for the column space of this one. So look at, so we have 1 2 3 with a leading one, right? And look at this column, say column 1 2 3, so say column 3, so column 1, column 2, column 3, column 4, column 5, column 6, and the column 1 2 and 4 has a leading one, right? Column 3 can be written as linear combination of column 1 and 2, right? 3 times column 1. Example, column 3, say they are all vectors, say. Column 3 can be easily written as linear combination of column 1 and column 2. So it's a 3 times columns 1 minus column 2, 3 times, right? Column 5, for example, can also be easily written as linear combination of column 1, 2, and 4. So example, column 5, 2 times column 1 minus column 2 plus column 3. Column 4. So look at this. 2 times column 1 minus 1 times column 2 plus 1 times column 4. Right. And we do the same thing for column 6. Right. Column 6 can also be written as linear combination. So column 1, 2, and 4. So what is this? 3 times column 1 minus 1 times column 2 plus 1 times column 4. Right. Column 6, 3 times column 1 minus 1 times column 2 minus plus 1 times column 4. Right. So look at it, you can easily get column 1, column 2, column 4 is form a basic for the column space of B. Right. Column 1, column 2, and column 4 is a basis of the column space of the matrix B, the reduced row echelon form matrix of A. Okay. And as I said before, the matrix A, so we know this matrix A. This matrix and its reduced version might not have the same, usually they don't have the same column space. However, they do have the same dimension for the column space. And the corresponding column, so column 1 for matrix A, the first column 1 for matrix A, can write there, column 1 for matrix A, column 2 for matrix A, and column 4 for matrix A. They form a basis for the column space of the matrix A. Let me write down. Here you have, say, vector, say V1 correspond to the first column vectors V2 and V4. V1, V2, and V4, they form a basis of the column space of A. We call that V1 is the first column of A, V2 second column of A, V4 the last column of A. And this is because elementary rows operation do not affect on the dependency relation of the column. The dependency relation between column vectors of A